warm welcome after the coffee break. Unfortunately, the two presenters from Simontech didn't get a visa, so instead of the dark side of the WebAssembly, we hear a very interesting presentation about Android app deobfuscation using static and dynamic cooperation from Yoni and Yaniv from Checkpoint. Thank you.
Viele Tische. No. Good morning, everybody. Thank you for joining. We're here to talk about mobile threat detection. I have two kids, and for quite a long time I had bad feelings that my kids cannot come to the kindergarten and say something like, "My dad is a firefighter." But quite recently, my 6-year-old son approached me and said, "So, Dad, are you kind of a computer's policeman?" I chuckled, did feel a little bit proud, and thought about it and said, "Well, maybe not quite a policeman, more like an investigator, Sherlock Holmes." For us, threat prevention on mobile is our day-to-day job. We proudly hunt malicious Android applications for a living. My name is Yaniv, nice to meet you. My dear friend here is Yoni Moses. We're security researchers at the Mobile Threat Prevention Group in Checkpoint. And as security professionals, maybe not yet. Okay. So as security professionals, our main task is to protect the mobile devices of our users from any malicious activity that might happen there. And to do that, we have to process enormous and ever-growing volumes of applications, searching for increasing numbers of malicious behaviors. And, well, naturally, the only viable way to process all those volumes of data is to rely on automated processes, automatic types of analysis. And the precision and ability to scale those processes are the things that actually define our success. So while we as security researchers usually want to deal with a new zero-day or to find cool and sexy new vulnerabilities, the reality is that our success is mostly defined by our ability and our tenacity and scalability to actually find all the vulnerabilities that were there ever and still mostly are relevant on very big volumes of data and devices and users and companies. Through the course of the last year, we a little bit departed from our usual let's find new vulnerability kind of approach to mobile threat detection. And we invested a lot of effort in developing new and quite innovative techniques that actually allow us to be much more precise and much more scalable. So one of these things that we are going to discuss now is deals with code obfuscation. But first, let's talk a little bit how our whole process works, because the real story here, there will be green text or black screens and code and sexy things, but the real story is the ability actually to have a research that ends in the production and actually brings that value to your customers. So our analysis process, I guess not surprisingly, works in cycles where first cycles are very cheap, take milliseconds, and we mostly there it ends. Like for the vast amount of attempts, it ends there. A millisecond, and we are done, and we know what it is, and we are good to go. Because mostly these are known things. If things get more complicated, we use more and more expensive cycles until it gets to cycles that take hours to complete. And there are various engines that work, those who seek for data, those who analyze that data, and all the kinds in between. But generally, we divide the engines into the static ones and into the dynamic ones. The static ones are practically those who behave in a way like a human that tries to read the code. It deassembles the applications and tries to understand what goes there in a very theoretical way, as a human being reading it printed on a paper. While dynamic approaches are the opposite. It's sandboxed execution of an application, and in general, we just sit on the sidelines and try to understand what goes on there. So the static analysis has its main advantage is that there is practically nothing that prevents from covering all the available code in the application for the analysis, because it just goes through all of it and reads it. But the main weakness of it is the dynamic loading, that if an application downloads actually parts of itself or a binary, additional binary, and runs it during its runtime, then static analysis has no solution for that, because it doesn't have that dynamic part. Also, the encrypted parts are problematic too, because the ability of static analysis to actually decrypt the data while it schemes through the code is very limited. While dynamic analysis is quite the opposite. It is very, very good with handling all the dynamic parts, because the application just runs. So if it downloads a binary, decrypts something, dynamic analysis doesn't care, because it just will, if application does something natural, it will just happen, and we just go on. But on the other side, dynamic analysis is quite poor with coverage, because to get to all the corners of an application, it depends on many various things. Either it's user interaction, like we have to click on buttons in a very particular way to get to some corner, and automatically it's very difficult to do. Or it's based on your location, on your device model, on your operating system, on other applications installed on device. And there are many, many factors that affect how applications behave. You all know applications that are very malicious in very specific locations, but it's just a punny game in all the rest of the world. So when you think about these two approaches together, they in a way, they complete each other. And it was, for a long time, very logical for us to think that, okay, if we can do all this thing not divided in like two huge approaches with different efforts, but do it together, then dynamic approach allows us to get, for example, all the binaries and all the decryption, while the static approaches can show what should be all the conditions and all the branchings to get to the whole coverage. And that's what we thought like 5 years ago. So I'm telling you very old news. Why did it take so long for us to get here? First of all, because it's very complicated. Each one of these engines is very complicated by itself, and saying that now we want something that is all of them together is almost impossible to do just like that. Also, these are very different skill sets. These are very different types of people who are good at these two things. Static analysis guys, they are mathematical, algorithmic guys that are good with data structures and traversing trees and graphs and things like those, while dynamic analysis guys, they are operating system people. Those are guys who recite Linux kernel for their pleasure at night. And also sometimes these two groups, as it many times happens with talented researchers, think that their approach is the best and all the rest is redundant and why to bother. So,
of course, static analysis is the better one, obviously.
I still prefer to recite Linux kernel at night. Eventually we got to understanding that we want that investment because we want to be much faster and much better on one side. On the other side, our engines were mature enough. I think that my slides are kind of progressing by themselves. Okay, but so maybe sometimes we'll get them back. So, and also our engines became mature enough that we felt confident enough to say that, okay, let's just, a leap of faith, just doesn't matter the timelines, whatever, just plunge in and let's try to do something good with it. So actually, we started more than a year ago with the first attempts. We first started capturing the binaries on the dynamic sides and transferring to the static side, which is technically quite easy to do because you just move files and there's very little interaction. Then we had research about unpacking, that dynamic sides unpacks packed binaries and passes them to static side. That was a very interesting research that was presented last year on DEF CON. And now it is in production, and we are very pleased with how it works. So this year we dealt with obfuscation, and the interesting thing with obfuscation is because there you cannot already solve it with this easy interaction of just take this file, take that file. It actually required all the engines to work in kind of a ping pong, like help me here, help me there, and the more interesting details, Yoni will elaborate.
So the focus today will be really how dynamic analysis actually helped static analysis deal with obfuscated code in Android apps. And why is it really an issue for us? Obfuscation is quite common in Android because, as you know, most of the code in Android apps is written in Java, which is really easy to decompile. And that's why many developers choose to use obfuscation. It can be a benign developer that just wants to protect their intellectual property from reverse engineering. And maybe it's a malicious author that wants to avoid detection. So obfuscation is an issue for us. I think do you hear a strange feedback too in the sound? Or is it just me? Okay. So the most common obfuscation technique would be renaming of classes and methods that the developer defined in their code, just renaming them to gibberish. It's not really an issue for automated static analysis because it doesn't rely on the meaning of names, unlike a human performing reverse engineering who obviously relies on the meanings of the names. But string encryption, especially when it's combined with function call by reflection, that's a serious issue for static analysis. And what do I mean by that? Suppose an app wants to use a sensitive Android API, and it wants to do so in a hidden manner. So instead of just calling a function with regular function call, it can call it with reflection and encrypt the name of the class and method that compose the API. And so static analysis can't follow this API call. Also, many other kinds of interesting strings can be encrypted, like path to content providers that provide access to sensitive user data, like text messages. So, okay, string encryption is a problem for static analysis. Why can't we just deal with it on our own without asking for help from these guys? Well, decryption in static analysis is possible, but it's hard. because all the information is already inside the app's code, right? Otherwise, the app itself wouldn't be able to decrypt the string on runtime. So the decryption algorithm is there, the decryption key is there, but I don't want to start implementing decryption algorithms in my static analysis code. And I don't want to come up with a way to automatically find the decryption key inside the app code during static analysis time. It's just too much hard work. So, okay, if we consider that decryption is done automatically when the app is run, maybe we should indeed ask for help from our nice friends in the dynamic analysis team and have dynamic analysis simply read the decrypted strings during analysis time and then pass them over to static analysis. So before we show how this actually works, let's first take a closer look on how string encryption looks in the obfuscated app. So a typical obfuscator would just take the string initialization code and wrap it with a function call to a function that was generated by the obfuscator itself. And this function basically returns the decrypted string. And it receives as parameters, I guess you can consider it as the encrypted string and maybe some kind of decryption key, this small number. And many times it would be a static function, which means it's not dependent on, I don't know why the slides keep moving on their own, but never mind. It's a static function, which means it's not dependent on any previously initialized objects. So this is how it looks like. So I guess the first naive solution we considered was just to have static analysis look for calls to these decryption functions. Maybe it's one copy of the function called several times. Maybe there are several different copies. Never mind. So just find them in static analysis and pass over a list to dynamic analysis. And then dynamic analysis could place breakpoints so that during runtime, it can save the return value, which is the decrypted string, and pass it over to static analysis. So basically, it's a nice idea. But if you recall, Yaniv mentioned a major issue with dynamic analysis, which is partial coverage. We don't expect, in this case, that dynamic analysis would be able to cover all string decryptions because it doesn't usually cover any possible flow in the app's code. So a better, more comprehensive solution would require a bit more work during the static analysis phase. We will not only find all calls to the decryption function, in this case it's the function here, bar. We'll also have to perform a backtrack search looking for the values of the arguments passed to the decryption function. In this case it's a constant string and a constant number. So that's not hard to do in static analysis. It's basically the basic stuff that we do. So now static analysis can pass to dynamic analysis a comprehensive list of all decryption function calls with the values of the parameters. So basically dynamic analysis now has all the information it needs to perform decryption on its own, to execute the decryption code outside of its ordinary context or flow. So what would happen, dynamic analysis would load the APK, but it wouldn't start the app yet. It wouldn't start the main activity. Instead, it would patch Android runtime to execute the decryption calls one after the other. And it would save the return values, the decrypted strings, in order to pass them on later to static analysis. And then static analysis can use the values of the decrypted string to sort of patch the code. What do I mean by patching the code? First, we just replace the function calls to decryption with the values of the decrypted strings. But if we also want to deal with the problem of function call by reflection, we want to changed these function calls to just ordinary function calls that static analysis knows how to follow. So we will look for calls to the method invoke API, perform a backtrack search to find the names of the invoked classes and methods. And by now these names have already been decrypted, so it's okay. And then we just replace calls to method invoke with ordinary function calls. So I hope it's clear enough, but if not, don't worry. It's just a basic example of how a patched code would look like. It's really a simple example without reflection. So basically what we have here is a piece of code that wants to get the device ID. And to do so, it needs, first of all, to pass the string phone to the get system service API. So in the original APK, we had the string phone encrypted, and now it's decrypted. So, as some of you may have noticed, there are limitations to the solution that we just talked about. So first, I think it's worth noting that for us, the most important thing wasn't to necessarily get the best, most comprehensive deobfuscation solution, but to really implement and deploy to production a feature that combines static analysis with dynamic. So it's okay for us that there are limitations, but let's just state them for the record. At the moment, it only works if the decryption function is static. It's not dependent on any previously initialized objects. And static and also receives constant arguments. And also we assume that the decryption function doesn't have any side effects, right? Because now it will run like twice instead of once. So just quickly about a little experiment that we did to test our approach. We wanted to start with a relatively simple obfuscator, -O. It's a commonly available commercial obfuscator. And the example we previously saw was of code that was indeed obfuscated with -O. So we implemented a signature to find -O samples. We found about 600 samples with -O string encryption in our APK database. And just a few examples of strings we found there. And so we ran our complete solution on these 600 samples, and we found that many of them had hundreds or even thousands of encrypted strings. And it was nice to see that static analysis detected new sensitive flows in 10% of these apps. I mean, flows that it didn't detect before when the strings were encrypted. So access to Google account credentials, text messages, user contacts. And 10% may not sound like much, but bear in mind that most of these apps are actually benign. So it's perfectly possible that they don't have a lot of access to sensitive user data. So easier said than done. We did have to face some challenges in the implementation phase, because first of all, static analysis and dynamic analysis weren't designed, in our case, to work together, and they run in different environments, because dynamic analysis needs a fancy Android emulator and static analysis doesn't. And also, dynamic analysis had to violate a kind of prime directive, which is kind of similar to the prime directive in Star Trek. Those of you who are familiar, you're not supposed to interfere with what you see, with what you discover. So dynamic analysis, usually you don't want it to interfere with the application's run, because then it makes it easier for malware to realize that it's being emulated, being analyzed. But in this case, we did interfere. And testing it also required an interesting infrastructure to run all these 600 apps on both dynamic and static analysis. So just a quick note about what happened when we deployed it to our production environment. First of all, it currently supports decryption of -O obfuscated apps and also some versions of DexGuard. And most apps we ran in production had just a few encrypted strings, but some of them had like megabytes of encrypted string data, which really caused interesting performance issues for us at first. And also the whole thing was much more volatile than you initially thought, because some apps are just not written very well. Maybe they only work well on some Android variants, so they just crashed in our analysis environment before we even managed to run the string decryption flow. But overall, it's currently working in our production environment, and the performance impact isn't very significant. So to sum things up, and I hope we'll have time for a couple of questions, back to Yaniv.
Thank you. Okay, so we were very pleased with our results. We're running it in production for a couple of months. For us, the main achievement was actual ability to get all the people together and do that and reach that stage where we just can actually engineer that thing. And the results were so good compared to like original skeptical views that there is a lot of hunger now to continue with this approach. So we are already working on much more sophisticated obfuscation techniques that actually do handle state and try to work with the more complicated situations where it's even not necessarily a function, because not all obfuscators necessarily create a separate function, so we have to handle actually pieces of code that we have to deobfuscate, and a lot of directions and things to do, hopefully next year. Thank you. If you have any questions.